Hello, Debbie. Can you see and hear us okay?
Can. How are you?
Doing good. I don't know why. Oh, I haven't split WebEx yet. That's why there's two on the screen. I'll mute that video so that won't happen. But as long as you can
We
see
don't
it.
have a double.
Do you
I
have
just see one. I just see one.
Okay, good. That's just on my end then. Can you share his computer to make sure it's up on the screen here?
I did. It should. What are you seeing?
I just have a blank screen right here there's nothing on the screen. It's like I see the light on the projector.
It's showed though. Can you see it now?
There it is. The computer must have gone to sleep.
Yeah, you have it.
We're good. Thank you, Debbie.
You're welcome.
Hey, Mike, you doing all right tonight?
Good. You?
Doing pretty good. Just wanted to let you know for sure that I've got the message that your homework in the outside mailbox.
I appreciate that, bud.
And also, just so you know, the calculus attendance will be in there with it separate. So there'll be two attendance sheets plus an envelope that has my stuff in it. Okay.
Hey, do you got the attendance sheet?
The what?
Do you have the attendance sheet for calculus also?
Yes, that's what I was telling you. I have those for today.
Yeah. Put that in your envelope too, bud.
Okay. Okay. Then it'll just be the envelope then that you get out. Perfect.
Thanks.
Yes, sir.
So the first thing is you have homework 7 for me. It's all right. It works okay. I mean, you can see what I graded when I sent it back to you, right?
Yeah. Mom says about the last problem. I'll try my best.
The other thing is, I'd like to go back to this for a second. So that's the project, right? That's not due till Friday the 26th at like 5 o'clock when the Dropbox closes. You know, you're not going to email that to me. You're not bringing it to class. You're going to upload that Word document to the Dropbox. The last call me and you did was 5, and I told you we couldn't do the bonus there until the end. And I have to skip over 6. Because 6 is what we're going to cover tonight. Remember, I jumped all over the book here anyway. And so we can actually do the last problem here, which is 7. And the reason is because it's a proportion problem. And it says, problem 7, question 12 of the survey must ask, if you had to lose one of your 5 senses, which would you choose? Hearing, sight, touch, smell, taste. Okay. Many surveys have been conducted on which of the 5 senses you want to lose if you had to lose one. One study stated that 57% of people said smell would be the sense they would choose. Some poll, you can go there and see what they said. Is the same true for the population of all U.S. college and university students? It says create an appropriate graph and display the distribution of senses and insert it here. Hey, what kind of variable are we looking at? That's always the question. When somebody asks me, hey, make a graph to show me the distribution of something, I always got to ask you what type of variable you're looking at, either quantitative or you're categorical, and here you are categorical, correct? So you've got 2 choices. You can either make a bar graph or a pie chart. And you know me, I'm always the bar graph guy. That's just the way my little head works. And so I just want a simple one. Remember, you've got counts of unique values, nothing summarized. You have the raw data. And I want, what was it, census? Can I ask you to do one other thing for me here? I don't know if I mentioned it the last bar graph we did, but can we take this and can we show y as a percent? In other words, the bars will be a percentage instead of a count. Just so we'll change up a little bit. So I click OK. OK. So you notice there's my 5 senses. There's the percentage that would have chose to lose that one. Notice which one's the highest one. Smell, and hell, it's over 60% there, isn't it? Yeah. Okay. So that's the graph you need. All right. So you'll copy and paste that. Back here, it says how many of the students surveyed said smell was the sense that they would choose to lose. Now, me and you've never done this, so I'm going to show you this. I need to go to Stat, Tables. Because I'm not going to sit there and count through all of them and tell you, okay, here's how many said smell. I'm going to go to Stat, Tables, Tally Individual Variables. What do I want to tally? I want to tally your senses. What this is going to do for me is it's going to tell me how many chose which one, right? To the 5. And you notice, does everybody see where it says display right here? It says display counts. And I'm also going to choose percents. So not only will it tell me how many in terms of the count that chose whatever category or whatever sense, it will also tell me the percent that chose that. And I'm going to click OK. So what I would do is I would copy and put that table there for me. Copy and put the table and then tell me, look, hey, I can see right here how many chose smell. 396. Everybody see 396 out of whatever it was, 635 chose smell. It said how many, right? So it wants the count, right? It says how many. And then part C says what proportion of our sample said smell. Well, shit, we already did that too. The percentage is 62.36. What's the proportion? 0.6236, right? So that one little table there, and then type in there, tell me there was 396 and the proportion is 0.6236. Then we come back and it says, assume for the purpose of this problem that we may treat the spring 2019 sample as a simple random sample, because they're getting ready to ask me to do something here, so obviously it's got to be a simple random sample, drawn from the population of all U.S. college and university students. Use Minitab to calculate a 95% confidence interval for the proportion of students in the population who would choose smell to the survey question based on the survey data. Now, I know you just turned homework into me where I made you calculate a confidence interval for proportion, but Minitab will also do it for us. So, again, I'm going to go a little slow here. I'm going to go to Stat, Basic Statistics. The reason I'm going slow is because the chapter we're going to do tonight, I'm going to come right back to this little spot. And you see right here where it says one proportion? See, this is a one sample proportion problem. That's the reason it says one proportion. So I'm going to choose that. And then it always comes up with one or more samples in each column, but we have to use the summarized data. And the reason is because, look, there's one outcome we consider to be a success, that is that they chose smell. The other 4 turned out to be failures for us, right? Because that wasn't the outcome we were looking for. The outcome we were looking for, the success, was a smell. If they chose something else, we consider that a failure. I have to do it this way. And when Minitab asks you for the number of events, what it's asking you is how many chose smell. Well, we got it right there. There was 396 chose smell. Everybody see that, right? Because you did that in part B or something, yes? And then it says the number of trials. It wants to know what's the sample size. In other words, 392 chose what we were looking for out of these 635, so we need to put 635 there. Everybody okay? Right? Number of events is the number of successes. The number of trials is our sample size here. And then I want to show you something here because we're talking about Minitab, and I know it's a proportion problem, but we're going to talk about it again. I want to start here. If I wanted to do a test of significance, you see right here where it says perform a hypothesis test. If I check that, it says the hypothesized proportion. You know, in the null hypothesis with a proportion, it's always P is equal to some value, correct? You know, P is equal to 0.2, or P, the one you just did for homework was P was equal to 0.5. You would put that value there. Whatever the value is in the null, right? That's what they mean by the hypothesized proportion. I want to uncheck that. I want to go to options and show you something here. I can calculate any confidence interval you want. If I click here, you notice it says 95%, and that's what the capstone one. I can do 99, 90, 98, 97. Hey, pick one. You can do any of them you want. It's 95. I would also like to notice that under the alternative hypothesis, we're not doing a test of significance. You notice there's less than, not equal to, greater than. Isn't that always our three alternatives? So based on what you've written down, you can pick. I don't need any of them. But what I do need to make sure of is, anytime I want to calculate a confidence interval using Minitab, let's say for proportion, the alternative hypothesis better be set at two-sided. If not, we're not going to be happy with what we get. And then the method, exact. Of course I want the exact. I'm going to click OK. If I got everything filled out right, what I want to know is, can everybody read this? It says test, I'm interested in the confidence interval. Method, P, the event proportion, the exact method is used, descriptive statistic, N, how many people are we looking at in our sample? 635. Events, how many said smell? 392. What's the sample proportion P hat? What did I do? Oh, I gotta fix it. You guys let me put 392, it should have been 396. You're going to do. Why did you see that so quick? Because I knew it was supposed to be 0.6236 and it wasn't. I'm going to click OK. Now I'm happy. N is 635. Events, successes, smell, 396. Sample proportion, P hat is 0.6236. Can everybody see the 95% confidence interval? Everybody see it, right? The 95% confidence interval was 0.584648 to 0.661441. You're going to copy and paste this part right here. That's what you want, that confidence, right? That's what you want over here. It says, copy and paste the Minitab output. Interpret your confidence interval. How do you interpret your confidence interval? We are 95% confident, or with 95% confidence, that the true proportion of the students in the true proportion of all U.S. college and university students that would choose smell is between, I don't know, I got to look at the numbers again, 0.584648 and 0.661441. We are 95% confident that the proportion of all U.S. college and university students that would choose smell is between 0.584648 and 0.661441. Look, that's the same way I interpret a confidence interval for proportional for you on Tuesday, the 1 week, right? Same. Please start out with, we are 95% confident that the proportion of all U.S. college and university students that would choose smell, or with 95% confidence, the true proportion of all U.S. college and university students that would choose smell is in your interval, right? Both of those are good. You're giving me the success rate, you're telling me the thing you're trying to estimate, and you're giving me the interval that Minitab did for us. Part F. What do you think? Do our results contradict the results obtained from the survey? The survey said 57% choose smell. Obviously, ours is higher. Remember, our proportion that chose smell was what? 62.36%, right? Proportion 0.6236. Or do they appear to agree with it? Now, I'm going to kind of go outside the lines here a little bit. And I'm going to come over here. What we're asking you is this. That's what we're asking. Based off of our p hat, what can you tell me? What should we do about this test? Well, remember, I've got a calculator, right? I got to know what this is doing. This again, 0.584648. 0.584648. The other one is 0.661441. Right. Now, do you remember I had you read in some homework problem about the connection between a confidence interval and a two-sided test? You didn't have to read it. I'm just asking. Remember me talking about that and saying you should check that out? The reason is because of this. See, I would like to talk to you about this. Does everybody know why I'm interested in the 5% level and the confidence interval is at the 95% level? Remember, the confidence level and the significance level are supposed to add to be 100%. Yeah. Now, all we got to do is, I got to look at this value right here. The one that shows up in the null, you know, the one we assume to be true to get us started to calculate our test statistic and our p-value. And I'm going to ask you, let's look and see about this interval. Is it in there or is it not? Is 0.57 between 0.84648 and 0.661441? And all of us know the answer is it's not in there, right? Notice 0.57 is not in here. Obviously. It's smaller, right? And as soon as it's not in there, what we do, we reject H naught in favor of the alternative. Remember, I'd given it to you about rejected in favor, right? So in other words, since that value that's in the null hypothesis is not in our confidence interval, and I should also say this, we do all of this at level, if you don't mind, I'm going to say at the 5% level. Alright? So yeah, I gave it to you in terms of, I'm looking at this two-sided test. We already calculated the confidence interval. Well, I can see that 0.57 is not in there, so what does that tell me? Well, as soon as I have this C and this alpha, and they add to 100%, as soon as I look at that value that's in the null and it's not in my confidence interval, immediately I reject the null and I favor the alternative. If it's in there, the data is consistent with the null being true, right? I'm giving it to you like big picture thinking here. That's not what I'm not wanting all this for your project, all right? What I'm wanting from your project is, do our results contradict obtained from the survey, or they appear to agree? Give me one. Do they agree or disagree? You see that 0.57? That's the survey. It's not in the confidence interval we calculated using p hat that we actually were given, right? So what do you think? One more time. I know you guys are always waiting for me to give you the answer and you never have to answer me. I know. Do our results contradict the results obtained from the survey, or do they appear to agree with it? got to be one or the other. I'm going to give it to you like this. If that 57 was in our interval, let me go the other way. I always get a little upset when people start writing solutions here and the wording they use. Since that 57 is not in that 0.57 is not in the interval we calculated, right? Our results contradict what the survey says. Our results are trying to tell you that that proportion, at least for, if we're going to assume that you guys are a simple random sample of all college and university students, that's actually high. Well, at least we know it's different, right? I'm telling you it's higher because of where the interval is in relationship to 0.57. So the point is this. What you're going to tell me is our results appear to contradict the results of the study because the 0.57 that comes from the study is not in the confidence interval that we calculate. That's as clean as I can make this, because if the 0.57 had been in there, then the way I would have said it, on the other side is, well, you can't reject the null, right? You can't favor the alternative. The data is consistent with the null being true. The data is consistent with the proportion being 57%. What I would tell you here is our results in that case appear not to disagree. Sorry, it's just like that. You don't have to worry about that side because our results actually contradict the survey. This is here for you to show you what we're talking about. That's what we're really doing. Nobody wants you to write the test down. They want you to tell me that that 0.57 that comes from the survey is not in the interval you calculated. So you don't believe the null, you believe the alternative, which means back here, our results appear to contradict the results from the came from the survey. You don't believe the survey. Okay? Are we okay with this problem? We have to do this one. We can't get it. I know I'm going to stretch it out. Sorry. I mean, I would like to have been done 2 weeks ago myself also. Unfortunately. Okay? So that's that. So that gives me everything except number 6 in the bonus. I don't want to get rid of that. I'm going to need Minicap tonight because you are done seeing me calculate anything. Notice, did I calculate anything by hand here? No, I was interpreting, right? I didn't do the confidence interval or nothing by hand. I will do nothing from now to the rest of the semester by hand. Okay? So, with that said, one more time. Can everybody pick out the 95% confidence interval? I'm worried about the final, right? Because if we're not going to calculate anything by hand, you got to be able to pick out what you need out of a little mini tab printout. That's what I'm worried about. You know, okay, there's your 95% confidence interval. What do we do sometimes on the final? Oh, we can give you 3 of them. We give you the 90%, 95, 99, and it says give me the 95, and you've got to be able to pick out the right one. Okay. Where we're at is I'm backing up now to where I jumped over, and I want to go to chapter 20. And its inference about a population, 451, mean, and I'm going to put a mean there. And you're supposed to look at me and say, well, didn't we already do that? Yeah, we did. But when we did it, there was an unrealistic assumption. What's going to happen in this chapter is we don't know. In other words, what I'm telling you is sigma is not given. This is what really happened. Because again, if you don't know mu, there's no way in hell you're going to know the standard deviation sigma of the population. Now, first thought. All right? Anytime I start one of these new chapters, I always start with anybody know what number 1 is? Yeah, I always ask the question. I look at you for a second. Nobody says anything, and I always tell you, sorry, I didn't mean to giggle there, but at this point, you could have said, okay, anything we've done, you got some conditions, right? Usually there's 2 or 3, and number 1 has always been, yeah, it's always a simple random sample. Now, you and I both know that even though sometimes when you read the problems, the most it'll say is a random sample, right? And so then we're all happy with us going about our business. But all our methods are really true for a simple random sample. 2, the population distribution, you know, where you're drawing your sample from. We had insisted before that it was normal. We're going to relax that just a tad and say, at least it should be symmetric and single peak. So what we're trying to tell you in a roundabout way is this thing is going to look like a normal one. It's going to be symmetric and single peak and bell. I didn't write bell shape. It's going to be bell shaped. The problem is it may not satisfy the 68, 95, 99.7 rule, which all normal distributions satisfy, right? It will look like it's normal. It may not just satisfy that rule, right? So at least we can get away with symmetric and single peak. And I'm going to write number 3 like it is a condition, and it's really not. The catch here is mu and sigma are unknown. We don't know either one of them. Now, I'm assuming at this point you know mu is the mean of the population distribution, and sigma is the standard deviation of the population distribution. Now, when the conditions are met, X bar has a normal distribution. What I'm talking about when I just say X bar, I'm talking about the sampling distribution of X bar has a normal distribution, this one. Right? Boom. That's the one me and you used in the 2 chapters before this. Problem is, the fact that we don't know mu, you remember that wasn't a problem, right? The problem here is we don't know. We don't know. It won't be given to you in the problem. It won't be telling you, hey, the population standard deviation is 6 or 3 or 1 or whatever. It won't tell you, right? You'll know that. It won't be in this, all right? But what we're going to do is we will estimate sigma with the sample standard deviation x. Just like you can calculate x bar from the sample, you can calculate the standard deviation of the sample x. So, what do? We then estimate the standard deviation of x bar, and what I mean is the standard deviation of the sampling distribution of x bar. Remember, that is sigma over the square root of n by well, if you're going to estimate sigma there, you're going to estimate sigma over the square root of n by s over n. Now, this s over n has a name. S over the square root of n is called the standard error of x bar. Standard error because you are estimating the standard deviation. I gave you the same talk on Tuesday when I used p hat to estimate p in the standard deviation. Correct? I call it the standard error of p hat. Here's the standard error of x bar. Now, the thing about this is this little idea here, using kind of standard error to estimate a standard deviation, has not screwed us up. It didn't screw me up in the chapter about proportions. Unfortunately, in this chapter, it does change things a little bit. So there's something called T distributions. I'd like to circle that. Plural. T distributions. Okay? Now, we have been using, ever since we started in about a population mean or a population proportion, we've been using a z-score. And when we were dealing with the population mean, we were dealing with this. Right? That's how you calculated your test statistic when you were doing a test of significance. And I'm going to put here, this is when sigma is given. All those ones we did about the population mean before. Everything came down to a z-score. We had a z-star for our critical, this critical value in our confidence intervals. And remember, z has the standard normal distribution. And what makes it the standard normal is obviously it's normal, it's centered at 0, and it's got a standard deviation of 1. That's the one we've been using since chapter 3 when we calculated the z-score. That is your table A, right? That we look things up. We look at area to the left of the z-score. That's always our standard normal. That's what me and you have been doing for a while now. Here's the deal. When we use, and look, I'd like to, I'm trying to show you where things come from here. Remember, I'm still not going to do anything by hand, right? But I'd like for you to know, okay, where does this all come from? Is the reason I'm doing this. When we use the standard error of x bar, and I'm writing s over the square root of n, to estimate sigma over the square root of n. All right, so here, can we just be honest? What I've done is, I've replaced the sigma with an s, right? I replaced the population standard deviation with the standard deviation that can be calculated from the sample. That's what I've done here, right? I replaced the sigma with an s. The statistic, or the, I'm going to use statistic, is no longer a z-score. As soon as you make it where you're going to estimate the standard deviation, you're going to get this t. And how do I calculate that? That is exactly the same as before, right? The sample mean minus the population mean. Notice what's in the bottom. That's not the standard deviation. That's that standard error. That's s over the square root of n. This right here is a normally when I talk about z, that's a z-score, right? This is a t-score. All right, so let's be honest. What have I done? I've changed the sigma to an s, and I've changed the z to a t. Yeah? Other than that, I haven't done anything to you yet. Since I didn't know sigma, I had to estimate it. Well, when I estimate it, I obviously can't get a z because you get z when you use sigma. I get what's called a t. Here comes the punchline. T. That statistic t, just like z, does not have a normal distribution. Now, that's so disturbing to me. Oh, I ain't never wrote that shit for you. Everything me and you've done all semester, when I had to look at some normal, I even call them all normal curves, right? Every time I had to look at a density curve, no matter what chapter me and you was in, hell, it was always normal. This is the first time I wrote down that I'm going to do something here, and what we're going to look at does not have a normal distribution. This t does not. This t statistic, this t equal to x bar minus mu divided by s over the square root of n, does not have a normal distribution. That's a first for us. All right? Now, it has what is called a t distribution. That's one. Now, before I go any further, and I point us to this little box on page 453, I'm going to back up here just 1 second. And I want to look where I wrote this t-score down. Does anybody remember what a z-score tells me? The z-score always tells me how many standard deviations away from the mean a x bar is or an x is, right? And I always move my hands like this. Remember, if it's positive, it tells you, you got a z-score of 2.42, your 2.42 standard deviation is greater than the mean. Do you see that t-score? What that t-score is, it tells you how many, not standard deviations away from the mean, it tells you how many standard errors away from the mean. Because how do I know that? That's what you're dividing by, is the standard error. So if you get a t-score of 3.13, that means your x bar is 3.13 standard errors greater than the mean, right? Negative means you're going this way. You're going, why are you telling me that? Because when I did those tests of significance before, I always want to think about when your z is large, right? When I got a pass 2, I started talking large, yes? You have large t-scores also, right? That's my reason for going back and mentioning that. It doesn't tell you how many standard deviations, it tells you how many standard errors away you are. Now, what's on my mind is this. It's on page 453. We're almost where we need to be. It says, draw an SRS of size n, and it's always size n for us, from a large population that has a normal distribution with mean mu and standard deviation sigma. All right? We've been doing that all along. All right? There's nothing special there. What's special here is what I'm going to call the one sample T statistic. Before I talked to you about a one sample Z statistic. Now it's a one sample T statistic. It's this guy right here. X bar minus mu, S over the square root of n. So that you're not confused when I'm always talking t-score. That's a t-score to me. And it says, has the t distribution and there's one more little piece with n minus 1 degrees of freedom. Now, we denote degrees of freedom as df, and the df here is always one less than your sample size. Now, I got to remind you something. Me and you talked about degrees of freedom. It's all the way back in chapter 2. Every time somebody talks to you about in this case, the sample standard deviation S, there was always this degrees of freedom that was supposed to come attached with it. We never did anything with it. I mentioned it back there that every time you had 50 observations and somebody would calculate the standard deviation, there was always this degrees of freedom of one less than the number of observations, in this case 49, that came attached to it. It's back. Because you are using S now. So, we speak of the t-distribution with n minus 1 degrees of freedom. That's the way I would write it for you. Some people would write like it. So you might let me t4, right, or t8, depending on what your sample size is. There is a different t-distribution for each sample size n. Obviously. If n is 50, we'll be looking at the t-distribution with 49 degrees of freedom. If n is 20, we were looking at the t-distribution with 19 degrees of freedom. If n is 25, we'll be looking at the t-distribution with 24 degrees of freedom. You understand there's a connection between the degrees of freedom and the sample size. The t-distribution is always spoken about in terms of the degrees of freedom, which is one less than your sample size. Now, here's I guess this is probably the bottom line. I'd like to draw you 3 pictures all on the same. All right? So, I'm going to change colors on you because that's about as good as I can do. Anybody know what that is? That's the standard normal distribution, right? That's the ones where the z-scores live under. Yeah? And then I want to draw you 2 t-distributions just to get you a feel for what's going on. The book has this picture on the bottom, page 453, figure 20.1. I'd like to draw you one where the t-distribution with 2 degrees of freedom, which means how large was your sample? Your sample was of size 3, right? If it's 2 degrees of freedom, add 1 to get your sample size, okay? And it would look like this. I need to come down here, and all of these are centered at 0. And I'm going to label that as, that's the t-distribution with 2 degrees of freedom. The sample size n is equal to 3. Everybody follow, right? So they give me the sample size, I know the degrees of freedom. They give me the degrees of freedom, I know the sample size. Then I would like to go up and say, okay, well, let's increase the sample size a little bit. And let the blue one be, let's say the t-distribution with 9 degrees of freedom. Now let me ask you this. If I look at any one of these curves, the one in red, the one in blue, and the one in black, what's the total area of any one of these? 1. Always, right? It's density. The thing is this. They're all centered at 0. Right? So I'm going to leave that there, and I'm going to come over here, and I'm going to bounce back and forth. I've got 3 thoughts here. They're all centered at 0. Now remember, we're looking at one of them that's a normal distribution, and I'm looking at 2 of them that are t-distributions, right? They're all single peak. Bell shape. Oh hell, to be honest with you, they're all symmetric. Alright, look at it. Are they all symmetric? Yeah. Are they all single peak? Yeah. Are they all bell-shaped? Are they all centered at 0? Yeah. Okay? In other words, all 3 of these look exactly the same. Yep. Except 2. The spread of a t-distribution is greater than I'm going to go back to the picture. Right? So the spread, remember the spread is controlled by the standard deviation. The spread is this, right? So you notice the t-distributions are not quite as high at 0, are they? They're a little flatter, and there's a little more spread in them going this way, yes? Let me ask you, what are we estimating here? You're estimating the standard deviation. What's the standard deviation control? This. Yep. I always like to put this line here when I say more spread. What I mean is the t-distributions A t-distribution has more area in its tail. You're estimating the standard deviation, you're changing this, you're flattening things out. There's actually more areas in the tails of the t-distributions than the standard normal. If you would like for me to put it one more way, a t-distribution does not satisfy the 68, 95, 99.7 rule. That's what makes them not normal, right? They don't satisfy that. Hell, there's symmetric single peak and bell shape like every other normal curve we look at. They don't satisfy that rule. Why? They have more area in their tails, right? There are more spread to them. They're not as high on the hump because you're estimating the standard deviation. And then I've got a third thought here. Then I'll come back to the picture. As, can I use that for degrees of freedom and just write that, right? As df increases, in other words, as your degrees of freedom increases, and what does that mean? We're talking about if the degrees of freedom is increasing, the sample size is also increasing, right? So as your sample size increases, obviously your degrees of freedom is going to increase. The t distribution get closer and closer to the standard normal. Distribution, this guy here. So I'm going to think about this for a second. As the degrees of freedom increases, the sample size increases. What happens to the S as an estimate of sigma as the sample size increases? What's the law of large numbers say? It says as your sample size increases, your statistic gets closer and closer to your parameters, what it really says, right? So as your sample size increases, your sample standard deviation S is going to get closer and closer to the population standard deviation sigma. So I'm going to give you, obviously, the t-distribution is going to get closer and closer to look more and more, become closer and closer to satisfying the 68, 95, 99.7 rule. Now, I can show you this in a couple places. I tried to show you here. Notice, there's the standard normal. 2 degrees of freedom down here, 9's here. 15 would need to be getting closer. 20 would need to be getting closer. So eventually, hell, it's going to look so much like the standard normal, you won't notice the difference. One place else I can show you that. You're going to do, you're going to have performance and stuff? Yeah. What table me and you guys been using? We use table A, right? That's all about the standard normal, correct? And then, we've been at this table C here a little bit too, right? Remember at the bottom we were using Z stars, that critical value depending on the confidence level. Remember the confidence level was 95%, Z star was 1.96. We was reading those last two. Yep. I mean, you've used table C. That's where we got our Z stars for our confidence levels, or our confidence interval, yes? Look at the first column. What does that say? D, F. You see what it says across the top? T-distribution critical value. Oh, shit, that table I've been using on you is actually a T-distribution table. Here's what it means. If I look at one of these, just for example, if I look at, I just want to see that we can all follow a little bit. If I look at T-distribution with 10 degrees of freedom, in other words, I want to see df is equal to 10, and I want to look at that row. All right? If I look at the degrees of freedom being 10, your sample size is 11. Come over here and look at 95% confidence. If I go up that row, up that column, then the degrees of freedom here is 2.228. Everybody follow? What does that mean? That means if you're looking at the sample size 11, degrees of freedom 10, the t-distribution, to get 95% between these two t-scores, you have to go 2.228 to the right and 2.228 to the left. You got to go further out than the 1.96 we do with the standard normal. Why? T distribution's got more areas in your tail. And you have to go further out to get to 95%. Then come down the column. Come down to where you're looking at, say, 25 degrees of freedom, a sample size of 26. Read that column again, 95%. You come down to 25 degrees of freedom, and your t-score is 2.060. So in other words, to capture 95% where you're looking at degrees of freedom being 25, you got to go 2.06 to the right, 2.06 to the left. Going down this column here is as your sample size is increasing from 1 all the way down to 1,000. Well, look, when your degrees of freedom is 1,000, your sample size is 1,001. Look at the 95% column. If you're looking at 1,000 degrees of freedom, 1,001 sample size, your t-score will be 1.962. In other words, under that t-distribution with 1,000 degrees of freedom, you got to go 1.962 standard errors that way, 1.962 standard errors that way. How far are you off from the z star we've been using, 1.96? You're off by 0.002. Me reading the table like that is exactly what I'm trying to show you here. As your sample size increases, the t-distributions do this. They get taller and taller. Hell, when you're looking at the t-distribution with 1,000 degrees of freedom, a sample size of 1,001, I can't even tell the difference between it and the standard normal. How do I know that? The table is telling me that. Am I the only one interested in any of this? I mean, I know it's a Thursday. It's Market Friday. Where's this place? Somebody pointed that out to me. That's how much I know. So here's the deal. All of this is about t-distributions. Why? Because I didn't know sigma. I changed one letter, a sigma to an s, that caused my z to go to a t. Right? There's a family of t-distributions. You pick the one out by telling me the degrees of freedom. Now, sometimes I'm a little reluctant to write down the formulas at this point because I'm not doing anything by hand. But what I would like to do is this. And then we'll look at a couple problems and we'll see if we can interpret. See, here's the thing. The interpretation can't be the problem here. Because the confidence interval is still interpreted the same. Right? Still the same. Always the same. The p-value out of your test is still interpreted the same. That's not going to change. Right? What's going to change is how are we going to get our confidence interval and how are we going to get our p-value. That's off the software. So the interpretation is exactly the same. Now, I'm on page 455. Okay? And I've got what's called the one sample t confidence interval. All right. One sample t confidence interval for Q. It looks like this. In other words, it looks like a estimate plus or minus I always promise you they look like estimates plus or minus margin of error. So I like to write, hell, X bar is through your estimate. Your margin of error has changed a little bit, right? Because we're not looking at z-scores, we're looking at t-scores. See, that t-star is called the critical value, and it's coming from the t-distribution with n minus 1 degrees of freedom because your sample size is going to be n. Right? And so, in other words, it's this. Just for the sake of things. Can I just show you one thing, and then I'm not going to do it by hand, but let's say we wanted to do a confidence interval. And let's say the confidence level was 90%. Okay? just for the sake of it. We're going to do a 90% confidence interval for population mean mu. So when I see that, the first thing I'm looking for in my problem is can I find a sigma? And when the answer is no, then I can't use what we were doing before. And so let's say my sample size, just for the sake of it, is 25. Right? No, okay, somebody gave me a sample size 25. They calculated X bar for me. What's your degrees of freedom here? I just want to make sure. It's always one less than your sample size, right? So it'd be 24. Yeah? Be okay with that. It's always one less than the sample size. And then, just to show you where I would come up with that guy, we would get that off of table C. And what I mean is this. I just want to make sure you can read the table, just in case somebody had to. So I'm going to table C, and if I've got 24 degrees of freedom, right? So I'm reading that very left column. I'm going to read 24. I'm going to read across and make sure I get 90. And when I read up 90 to 24, my little T star would be, everybody see 1.711? Abby, I get that right? So this would be 1.711, where normally we would use the Z star being 1.645, right? The reason I wanted to show you that part is Minitab's not going to show you what they're using for the formula and all that stuff. And my point is this. You understand, we might have to calculate that. There's your sample size. We could get the software to calculate that. I just want you to know where my T star would come from. That's all. I would never force you to do it like that, no. But I just want to make sure you know where it comes from. All right? So that's what my confidence interval looks like. X bar plus or minus T star times S over the square root of n. And what about if we look at, let's see if we look at the homework for a second. Oh, well, hell, let's just pick a problem out of it. I don't want it all the way to the back. Let's say we're going to do this. I'm looking at page 457. All right? And I'd like to look at problem 20.7. She sounds tall. Presented with recordings of a pair of people of the same sex speaking the same phrase, can a listener determine which speaker is taller simply from the sound of their voice? 24 young adults at Washington University listened to 100 pairs of speakers, and within each pair were asked to indicate which of the two speakers was taller. Here are the number correct out of 100 for each of the 24 participants. Now, you understand? You had 24 people do this, right? And then each one of them, they listened to 100 people, and then they chose who was the taller, and that is the number of correct out of 100. Assume these young adults can be an SRS. Thank you. The 24. Of all young adults, using a 99% confidence interval to estimate. Yeah, I'm writing it all out for you where I normally don't. Just I want to make sure you understand what's in the problem and what's not. To estimate the mean number correct in the population of all young adults in the United States. Now you understand that's a mu, right? How do I know that? You're looking at the mean of the population, right? You're looking at the mean number correct in the population of all young adults in the U.S. You got a sample of size 24. And it says, all right. So then the question is can I get Minitab to do this? I hope I can. Where you're going to go to is, I got to find this file, and I got to find chapter 20, and I got to find 20.7. So I'm hoping it's in my little mini tab files here. Chapter 20, 20.7, the file is tall. And what I should be seeing here is, I should see what, 20 of the 24, and then that's the number correct, yes? That's what I should be seeing. Everybody okay with that? So that's just the data there, putting somewhere I can use it, all right? No, 65, 61, yes, that's the right file. Then I want to go to stat, basic statistics. This time it's not a proportion problem, it's a mu problem, it's a t problem. So I'm going to go to one sample t, and what I want to do is, I don't have summarized data, I have one or more samples in each column. I've got the number correct. Okay? No, I knew I was in trouble. Because you're telling, that says Z, don't you?
Yeah.
You see right there? I knew I was in trouble. It wants to know the known standard deviation. And I meant to ask you, did anybody read sigma anything in the problem? And the answer was no. So the dude chose the wrong one. I'm willing to be corrected. Thank you. Stat, basic statistic, one sample t, second one down. Yes? Still the same. You notice it's not asking me for sigma now. It's going to calculate all that shit for me based off of the data. Now, can I do this? Can we check options here? Because remember, I showed you that earlier with the P, right? You can choose any confidence level you want. And what did I want here? I wanted 99, correct? One more time. Anytime you're trying to get a confidence interval out of Minitab, normally always when you come in, the alternative hypothesis is set to not equal two-sided. Make sure that it is. That you didn't do something strange, because you're going to get a weird answer if you don't have it as two-sided, not equal to, okay? So if I click OK, this tells me a bunch of stuff. It tells me my sample size is 24. We know the degrees of freedom is 23. We know the mean, x bar, is 62.17. We know the standard deviation, little s, is 5.81. Does everybody see that SE of the mean? That's S over the square root of n. In other words, if it'll let me write, there's my x bar, there's my S. We got them all. Everything you would actually need to do it by hand is there. X bar, S, S over the square root of n. That's the standard error of the mean, of your sample mean, of your x bar that we talked about at the beginning of this chapter. And then, everybody see that? So my confidence interval for the mean number correct is from 58.84 to 65.49. Are you looking at the answer? You're looking at me like I did something bad. All right, no, suppose I didn't do anything bad. Can we interpret that? Well, I'm going to come back here, and I got 58.84. Right, so all I'm going to write down is, okay, well, so what was the interval? It's 58.84 to, I read the comment as 65.49. All right? Now, what's our interpretation here? How would I say this to you? We are 99% confident. Remember, it was a 99% confidence interval that the mean number correct in the population of all young adults between, what was it, 58.84 and 65 point something, 65.4. Now, I always told you, anytime I calculated the confidence interval, I would write a statement for you, right, that you could say, whether the problem asked me for it or not. I got to underline a couple things. You just gave me your success rate. We did it at 99%. You just told me what you were trying to estimate. What was the final thing? We spit out the confidence interval that Minitab did for me. Are we okay? Right? So there we had the raw data. I showed you how to get Minitab to calculate your confidence interval. I got to go back to Minitab before we go. Because some of the problems, whether you're doing homework problems or whether you're working in learning curve, don't always give you the raw data. Sometimes they give you the summarized data. In other words, they'll give you the N, they'll give you the X bar, they'll give you the S, and then they're going to ask you to do a confidence interval. So I'm going to go right back to where we were. I'm going to clear your ink. I'm going to go to Stat, Basic Statistics, and make sure I get the one sample T. And I'm going to change. I don't have, let's say for the sake of things, I don't have everything. All I've got is the summarized data, and I'm going to choose summarized here. You notice what it wants to know from us. It wants to know your sample size, your sample mean, and your sample standard deviation. Well, I'm going to tell you that that is 24. I'm reading the left-hand side there, right? Maybe that was all I had. And my sample mean is 62.17, and my standard deviation is 5.81. The point is, Minitab will do it whether you have the raw data, which is the first one I showed you, or whether you have the summarized data. Let's make sure we get the right confidence interval. We're still at 99%, right, because we were already there. I'm going to click OK, click OK. It doesn't even look like anything changed, does it? Oh, but it did. That was the first one we did. It's the exact same. It'll give you the exact same answer whether you've got the raw data or you've got the summarized data. I'm just warning you, because some of the homework problems here, remember, I'm not picking up any more. Maybe some of the problems in learning curve that you're going to do out of this chapter, you'll have to do the confidence interval. Do not do this shit by hand. Get Minitab to do it. And whether you have the raw data or the summarized data, you can do it. The other thing is this. I mean, I want to cuss at you, but my wife tells me I'm not allowed to. That's the same statement I've been making for days. Right? The only thing that got easy for you, everybody's going, dude, why didn't you show me this 3 weeks ago? They won't let me. Because normally that was the hard part, right? Was coming up with the confidence in it. And we can do it by hand as long as you've got sigma. Of course, that's not really what happens. What really happens is what I just did to you here. But supposedly, that's supposed to help you understand the interpretation I use because it never changed. It doesn't matter how I come up with my confidence. One more time. Everybody's seeing this problem. They didn't give me a sigma, right? Nowhere did it say the standard deviation for the population sigma was equal to whatever. It had to be a T procedure. Okay. That all looks very, very similar to me, other than getting Minitab to do it. My interpretation was the same. So then I come over, well, if I can do a confidence interval, a T confidence interval, okay, there must be a one sample T test. Because what we've been using before really was a one sample Z test. That was your test statistic. Now, anybody remember the null? It's a statement that mu is equal to some value. That value, that mu subscript with a 0 comes from the problem. Well, now you're going to have the one sample T, and I'm going to add a word in here, test statistic. Well, if the T-score we discussed earlier, it's going to be this. Right? S over the square root of n tells you the number standard error. You see this? Just to show you we're doing the exact same thing. Assume. That's how you know we're assuming it to be true. We're assuming that that sampling, that T distribution is centered there. Our sampling distribution is centered there. We're assuming that H naught is true. Now, are we going to calculate any of this by hand? Does everybody know my three alternatives here? One of them would be, another one would be, those are the one-sided ones, right? Those are the same ones I've written down twice for you already. And then one of the other possibilities is, that'd be the two-sided test, right? So, your p-value is still exactly the same. That's the probability calculated assuming that H naught is true, that you take your test statistic takes a value as extreme or more extreme than what was actually observed. I'm looking at the areas in the table, right? Same as before. The only difference is, we're not going to look at that t-distribution and try to figure out, okay, so what is the area in the tail? Manytab's going to spit it out to me. It's not going to give me a z-score, it's going to give me a t-score. If you want to know where this little box is, there's a little box here. This is on page 457. It's the same pictures about how to find your p-value that have been in proportions and have been about mu when we were given sigma. So what I need here is I need a problem, and can I do the tall one again? We did the confidence interval already, right? So if I come over here and I go to page 460, and I look at 2010, it's she sounds tall continued. That's the one we calculated the confidence interval for the number correct out of the population of all young adults. Do the data for exercise 20.7 give good reason to think that the mean number of correct identifications in the population of all young adults in the United States is greater than 50? Now, did anybody hear me say the word evidence? No, and that was my trigger all the time. But it says, good reason. If they had been nice to me, they'd have put good evidence. As soon as I see that, I think, now, I can write down n is 24 and all that shit, but I'm not doing anything by hand here. I mean, I know my sample size is 24. I don't see a X bar, I don't see a sigma, I don't see anything, right? So this has got to be one of these t-tests. So what's the first step every time me and you do a test of significance? A hypothesis. I told you before that that's always my template when I'm making claims about a population mean. It doesn't matter whether I know sigma or I don't. That doesn't change. What do we have good reason to see? We have good reason to think that the mean number of correct identifications in the population of all young adults in the United States is greater than 50. You're looking to see if you got evidence that the mean number of correct is greater than 50. Whatever value goes there, goes there. Now, step 2 is always my test statistic. Your test statistic here is a t. Unfortunately, I ain't going to calculate it by hand. I'm going to go here, and I'm going to come up here, and I'm going to go exactly where we were. Right? Because, I still have the same file here. One sample t. I'm going to go back and do it this way for you, where I actually have the raw data, right? Samples are in the column. And I want to do a hypothesis test. Now, whatever value you put in there, that's supposed to be what mu is equal to, right? The hypothesized mean. In other words, what are you assuming to be true? And what we're assuming to be true is, did I pull that out of thin air? U is equal to 50. Yes? Everybody okay with that, right? So that value that's in the null goes in the hypothesized mean. They can't write H from naught. They got to be fancy and say, okay, so what's the hypothesized mean? What are you hypothesizing to be true? U is equal to 50. You got to go to options now. I don't care about the confidence level because I'm not doing the confidence interval. I care about your alternative. Notice there are three. Less than, not equal to, greater than. What one do we want? How do I know that? The null is, alternative is mu is greater than 50. We tell it okay. We tell it okay. All right, so notice it gave me all that one. You know, there's my X bar, there's my S over the square root of n. Here's my warning about you get some crazy shit if you don't get a two-sided test to get your confidence interval. It only gives you like some kind of bound. So remember, anytime you get the software to do the confidence interval, you need two-sided tests. And then what I'm interested in is notice what it tells me down here. What it tells me is, hell, it knew more about what we were doing than we knew what we were doing. There's your null, there's your alternative. They don't write a little a, they put a little 1. The little 1 means you're looking at the alternative. Here is your t-score. There is your p-value. So I'm going to come back here and say the t-score was 10.27. 10.27. What does that mean? That means our x bar is 10.27 standard errors greater than the mean. Is that large or small? Yeah, this is where I really say a really bad word. That's gigantic. Right? I mean, if that was a z-score, you'd have said, dude, how'd you do that? Right? This is huge. This is what we would call large. Now, if that had been minus 10.27, and if you were to the left, I would still be telling you that that is huge. The plus or minus just tells me the direction, right? And then 3 is supposed to be your p-value. And in this case, the p-value is, look, I can't tell you it's equal to 0, even though it's telling you it's equal to 0. You and I both know it's not equal to 0. It's approximately 0. So is approximately 0 small or large? Yes? Remember, large values, your test statistic will produce you small p-values. To be honest with you, every time I do a test, I'm hoping for large values in my test statistic because I know that's going to produce me small values in my p-value. So that when I get to number 4, and what is number 4? See, there was no significance level here. Number 4 is I'm going to keep track of what we got here. T is 10.27. Your P is what do you want to do? And what I mean is, do you believe the null? Or let me put it this way. Do you believe the alternative, or do you think the data is consistent with the null being true? Is this one of the ones where you want to reject the null and accept the alternative? Is this one of the ones where you want to say, oh, I can't reject the null? I'm going to give it to you very simple here. I would like to reject H naught in favor of the alternative. Now here's the thing. I can't leave that as an answer. That's my general statement when I see a small p-value. In other words, what I would tell you is you've got strong evidence, as strong as you ever wanted, at any significance level anybody would care to ever ask you about. Strong evidence that the mean number correct is greater than 50. And you know, I should also be saying, you know, in the population of all young adults in the United States, we got strong evidence in favor of the alternative. I got all the evidence anybody ever wanted me to provide that the mean number is greater than 50. Now, anybody remember matched pairs? Where did we talk about that? I can't remember the chapter numbers, but we talked about matched pairs. Well, there's something called matched pairs T procedures. Matched pairs is an experimental design for us, right? Where there's only two treatments, and you match the subjects as close as possible, where you treat each subject as a pair. What you're going to do is you're going to find the differences between the responses to the two treatments we know we're looking at. Right? In other words, we know there's two treatments. So we're going to look at the differences between treatment 1 and treatment 2 and apply the one sample T procedures, which means the test and the confidence interval, to these differences. I know it's time to go home. When we come back on Tuesday, there's two things I need to do in this section still, or this chapter. One of them is I need to show you some matched pairs problem, how to set it up, what's the language. And the other thing I need to do is when do I get to play all these games? Yeah, I mean, I know I needed a simple random sample and this or that, but there's something about the sample size telling me what I can get away with. All right? Now, I want to put one thing down here in a different color. Because with matched pairs, you're going to take treatment 1 minus the response of treatment 1 minus the response of treatment 2, or you can flip them either way, just as long as you know how you get the subtraction. So, the language is, we're looking at the mean of the differences. I know, you're going, well, who cares? Yeah, the language makes a difference, right? You're not looking at, I don't even want to say it, we're looking at the mean of the differences. In other words, that is going to be your mu. There's only going to be a single mu here, even though there's two treatments and two responses. Mu is going to be the mean of the differences of the two treatments, right? So the language and the order of the words here are very, very important. Mean of the differences, because on Tuesday I'm going to talk about something else called the difference of the means. And you're going, dude, really? Which way you say that makes a difference? You've been with me 2 semesters. Is the word going to make a difference? Damn straight it does. The mean of the difference means I'm looking at a matched pairs, and I've done the subtraction up front, and now all my data is these differences. When I get to the next chapter and I talk about the difference of the means, there's two means. There's two means. U1 and U2. It makes a difference, right? So I want that. I'll show you a problem on Tuesday, and then we need to talk about my statistician friend. Hey, how much can I get away with and trust me? That's what we're going to talk about. It depends on the sample size. Be careful going to the house. We will see you on Tuesday. We'll do that, and we'll do problem. Well, what am I missing on the project 6, right? The 6, we'll do that too. I can do that when I come in and get in class on Tuesday, right? And then we'll do this, and then we're going to go to chapter 21, where shit gets all haywire at that point, and I got like 2 of everything in sight. All right, be careful. We'll see you on Tuesday.